First of all, let me thank each and every one of you, especially the authorities and the teachers of at the St. Aloysius College for inviting me to participate in this seminar. I was told that there will be students who are PUC students also in this meeting. Therefore, I thought that I will keep the talk probably at a level where they also will be very comfortable with. We primarily talk about vectors in this lecture, and then how to express an equation of a straight line in the form of in terms of vectors. Now this is the theme of it. I don't know how far I can cover. Vectors occur in physics. In fact, the origin of vectors, the idea, the concept of vectors originated in physics. In fact, you are aware that there are displacements, velocity, acceleration, and force. These are the four different types of vectors that you are very frequently coming across in physics. And this has been mathematically modeled geometrically in the following way. What is significant about the vectors? If you analyze any of these four quantities that you often come across in describing dynamics, you see that there is a point where the vector acts, like force acts on something, velocity acts on something, there is some object carrying the velocity, etc., etc. Then there is a direction in which it acts. Thirdly, it has got a certain magnitude in terms of some scaling norm that you accept. So you have an object with a point of action, then a direction and magnitude. Now this has been mathematically conceived in the following way. The point of action is, see, vectors are in general three-dimensional in the space, but we will put it on the board, it's a two-dimensional space. So let us see this. So you have a point of action, and then there is a direction in which it acts, which is marked by an arrow, and then we keep the length of the line segment that we have drawn to be proportional to the magnitude of the vector. So this length is there, so we call this point of action as O and A. So we call this a vector, and if you want you can write this as 3. Now let us consider a physical situation of a boat being rowed across the river. Now you know that the river flows. So there is already a certain velocity in the media in which the boat is going to go across. And that velocity will certainly act on the boat. Okay? Apart from that, the oarsman rows the boat, and suppose his objective is to see something like this. See, this is the river, and you want to go from this bank to this bank, and maybe this place from A to B you want to go. Something like this. Now you know that, assume this water is flowing in this direction. Now if you want to move from A to B, if you row the boat in the direction in which you want to go, what will be the result? There will be a velocity acting in this direction, there will be a velocity acting downwards, so essentially you will be drifting to a totally different point. And in fact, how this is overcome is with the native wisdom. The oarsman, he is not a person who has done a course on dynamics or anything. With native wisdom, what he does is he rolls it in some direction like this, so that all the time your boat will be keeping the direction from A to B. So he will be rowing in a direction in the opposite to the direction in which the water is going. So that now you see you have essentially two velocities acting on it. One, the velocity imparted by the velocity of the media, that is water. The other one, the velocity that we have imparted here, which is represented by a vector. Therefore, the problem is that you see these two vectors act on this and combine together to give a certain velocity in the direction from A to B. How does this work? Now, this is the so there should be some way in which they add up. Now we are first trying to decode this. How vectors add up. So that's the first problem. See, after reducing it to a geometric line segment, this is the first level of mathematical modeling. It's a geometric model that you are constructing. How do the vectors add up? This is the first problem. Let us try to resolve this. Now, this is not something that mathematicians can resolve. Okay? Because nature does not obey mathematicians. It has its own way. What we do is, we create a mathematics that suits the description of nature. Okay. In this regard, you would probably recall an experiment that you did in your class 11 or class 10 or class 11 or class 12. I don't know which class it is, or even later, a physics experiment in which you see two pulleys clamped to a drawing board, and then you have weights, 3 weights attached to it, something like this. These are two pulleys, P1 and P2. Then this is a point here, and there are 3 weights attached to it. One weight is acting like this, there is a third weight acting like this. So you have got W1, W2 and W3. 3 weights are acting. Now you see that imparts a force in this direction. A force in this direction. This is due to W1, and the function of the pulley is to change the direction of it. And then this is the third force that is acting. And at some point of time, this point comes to equilibrium if the weights are of the proper combination. It is at that stage that you normally put a drawing paper behind it, and then mark out these directions. What do? You mark out the following directions. Just put it in yellow thing. See, you mark out this direction, mark out this direction, and mark out this direction. 3 directions are marked. Okay? You also do the following. What you do is, you mark lengths along these directions proportionate to the weights that are that act along those directions. Okay, so you have a weight W1, say grams, or W2 grams and W3 grams, say, or kilograms, or whichever unit you are to use. So let's say W1 units, W2 units, and W3 units. Now you will mark out a length L1, say, let me designate this by A. So then the length of OA, L1, length of OB, is L2, and length of OC is L3. Mark these lengths. These lengths are proportional to this, by which I mean you have L1 is to L2 is to L3 is equal to W1 is to W2 is to W3. So we mark out the points A, B, C here. What did we do in those experiments next? So abstractly, what you get would be on the drawing board a picture, something like this. I'll take out this, and now I am on the drawing board. This is what I get. Okay. So I have three directions: OA, OB, OC marked. Then one observation. Now this is the ingenious part of our ancestors who solved this problem. One observation, that too after studying a lot of experiments, that's how they come across. This is a controlled experiment that you do. Okay. This point is in equilibrium. They observe that if you were to complete the parallelogram with OA and OB as sides, then you get a parallelogram marked out in your paper. So you call this point D. You make two observations. Now these are observations. We are working with physics actually. Observations. That the diagonal of OD of the parallelogram is along the line passing through O and C. What I meant is that if you take the diagonal here, see this line and this line are along the same line, so this angle becomes what you call pi. Okay, that is one thing. A second observation that you make is this: the length OC equal to the length OB. What do you infer? In your experiment, you found that the point O is in equilibrium. There are three forces acting on it. One along the direction OA, another one along the direction OB, another one acting along the direction OC. They act on the same point and keep it in equilibrium means what? the sum of any two forces has to be equal to the third one. Okay? So, here you have seen that OA and OB adds up to a force OD. So, these two forces can be replaced by the single force OD. And this OD acts in a direction opposite to OC. That is one thing. And the length OD is equal to OC of the length OC, which means that these two forces are equal and opposite, and therefore they cancel out, and that is why O is in equilibrium. Now this is purely an experiment. It's a beautiful experiment, in fact, with deeper ramifications. And in fact, the wild guess that the physicists made while studying various problems, that vectors add up to give the using the so-called parallelogram law is being experimentally verified through this particular experiment. I am sure that students would have done this. And what do they do in the physics lab? They repeat it. They repeat it by varying the weights W1, W2 and W3. Then you get other figures of different, because once you vary W1, W2, W3, you get another configuration of the same kind, but now quite different. The direction of OA and OB may be in quite a different direction. OC, of course, vertically down. And then you see that once again you verify that if you complete the parallelogram, then the diagonal is equal and opposite to the OC that you mark in the case. So you repeat these experiments 4 or 5 times, or when the physicists were formulating, first of all, this observation was a startling observation, and once you get a startling observation, they would have tried to verify this. They would have done the experiments hundreds of times or even 1,000 times. They would have repeated, not only in one location but in several locations, and then confirmed that in fact they can say that these two vectors add up using parallelogram law, by which you mean if you complete the parallelogram with these two vectors as the sides and draw the diagonal, that is the resultant of these two, OA and OB, and which acts equal and opposite to OC. Okay, so this observation they would have done in several times and then confirmed the speculation, and that gives that confirms the law of addition of the vectors. Addition of vectors. Two vectors add using parallelogram law. Okay. Now you see this is a geometric thing. It's quite nice. Now you can transform this. You have made a geometric model of your physical problem in terms of drawing directions and so on. Now let us see how we can make use of this. Suppose there is a point where several forces are acting. Something like this, something like this, something like this. Let me draw some 4 or 5 forces. Okay. So there are 5 forces acting, something like OA, OB, OC, OD, and OE. Now, how do you get the sum of all these forces? What one does is to start adding these vectors pairwise. Okay. For instance, you take OA and OB and add them. What do you do? Our method is complete the parallelogram and then take the diagonal. So you see that, suppose I call this OF, then I can replace OA and OB by the single force. Right? Now what do? I add these two, OC with OF. I can complete the parallelogram again and draw the diagonal. So my drawing is not good enough. Okay, so this. Okay, so this is the diagonal. Now let me call this OG. So OG is the resultant of OC and OF. In fact, OC, OA, OB, OC added together would give you what is called OG. So I can just remove these two. Okay. And then what next? So I have now three forces left. So what do we do? Once again apply the same sort of principle. Take any pair of them, add, and then draw the diagonal. So let me call that OH. Now OH and will replace OC and OD and OG. Now I am left with two forces, namely OE and OH. What do I do? Complete the parallelogram. Something like this, etc. Maybe something like this. Draw the diagonal. I draw the diagonal. We call this OI. Now OH and OE are replaced by OI. So OI is the resultant of the 5 forces that was acting on. So this is a, you see, mathematically it's a very nice solution to your problem in physics. That is, you can draw pictures like this. One can find the resultant of several forces. In fact, in 3 dimension also you can do it. In 3 dimension, what happens is you cannot expect all the 5 forces to be acting in the same plane. But still, pairwise, you can draw a parallelogram. That parallelogram will lie in the plane created by the 2 vectors that are going on. So, you see, you can do the summing up and still get the resultant of all the 5 vectors. But this is a very cumbersome process, especially when you have, at least theoretically, we have solved the problem. But we have not, our solution is not something that can be very easily operated. So what do? We try to resolve this issue. Okay? So what is the moral of the story? The moral of the story is that 2 vectors add using parallelogram law. Okay, so that's the moral of the story. Now, how can you work with the addition in a more workable way? Okay, more easily manageable. Let us consider a 2-dimensional problem. In fact, when you are considering only 2 vectors, then it is essentially a plane, in a plane that you operate. So let us, okay, the next thing that you do is that if 2 vectors are given acting at the point O, OB, we can use parallelogram law to get the sum of these 2 vectors, and you get OC by completing the parallelogram OBCA, and then drawing the diagonal, you get the resultant of OA and OB given by OC. How would we manage this? So what one does here is the following. You are familiar with the Cartesian coordinate system. Okay. So through O, I introduce 2 copies of the real line. tie them up at O. Now I have a unit length. Okay. Once I introduce these two lines, I put them together orthogonally. Okay, so that this angle is 90 degrees. This is for convenience. It's not necessary at all, but it's for convenience. We do it orthogonally. Now, what you observe is that if you have a vector, the tip of the vector corresponds to some point in the plane. And once you introduce the unit distances, you see that this particular point has a coordinates, which is an ordered pair of numbers, say x, y. Okay? What does it mean? It means that if you drop a perpendicular to the line x-axis and this is the y-axis, then this distance is x and this distance is y. This is the meaning of that. Conversely, every point in the plane can represent a vector. So every vector can be represented by an ordered pair of numbers introducing a coordinate system. Conversely, every point in the plane represents a vector. So we make use of this idea. So accordingly, see, you have two vectors here. So OA, I take it as A1, A2 as a two ordered pair of numbers, and B, I have B1, B2, and C, of course, C1, C2. That is that. Right? Now the question that you ask is this: how do you arrive at C? By completing this parallelogram and then drawing the diagonal. So C is something that has come out of A and B or constructed out of A and B using parallelogram law. Using this OA and OB, we have constructed OC. Okay. And it has some coordinates C1 and C2, not something that you measure. So we will try to see. At the outset, you know that the coordinates of C are related to the coordinates of A and B. So this is something that I write. The coordinates of C which represent C are related to the coordinates of A and B, because you have OA plus OB added according to the parallelogram law is OC. Okay, so this is a natural thing to expect. So you just don't know what C1 and C2 is. Now the question that you ask is, what is this relationship? This is what you are asking. Okay. In short, you are asking, see, what you have is C1 and C2 are functions of A1, A2, B1, B2. This is what you have. What functions? This is the question that you are asking. Okay? Right? Let us apply some knowledge of pure geometry to solve this problem. Okay. Let me see, what I am interested in is, say, I will just draw lines perpendicular to the line OX. Okay, call this A, C, D, E, F. So I draw the lines BD, AE and CF. All the three are orthogonal to the direction OX. Okay. Next, what I do is, okay, let me see. So therefore, what do you know? OD is given by what is called the first coordinate here, B1. OE is equal to A1 and OF equal to, we name it C1, but what is it? This is the question. These are given. These are given. This is unknown. That's why I put a question mark there. OF is C1. We just call it C1. So what is C1 in terms of these numbers A1, A2, B1, B2? Let us investigate this. I mean, you see, in any mathematical problem, you would have some guesses and then you try to prove it. Okay? So what is the guess that you have? See, you guess that, see, OF is equal to OE plus EF. Okay? So that's what we have. I mean, that's clear. I mean, that's not a guess, that's absolutely true. So OF equal to OD plus OE. Sorry, OE plus EF. This is clear. There is no mystery about this. Okay? So this sum plus this sum is this. But what do you know? Let us know what are the writing all those things that we know. We know that we know OE. What is OE? OE is A1. But we do not know EF. Okay? Right? And this is what we are asking for. This we denote by C1. So this is the question. Wait, this equality is true. We are trying to find out what C1 is. C1 is A1 plus EF. So if you know what EF is, then your problem is solved. But how do you know EF? From the figure, there is no way in which you can do it. What you know is OD. OD is B1. So the guess that you make, this is where you make a guess. The guess that you make is that OD is equal to EF. Okay? So is OD, I put a question mark here, EF. And if this is resolved positively, that is OD equal to EF, then you are done. Because OD, you know, OD is A1. Sorry, OD is B1. Therefore, you immediately have C1 is equal to A1 plus B1. That is your expectation. Okay? But how to prove this? This is the problem. Now, this is where your basic skills of pure geometry will come into play. Okay? Now, you have how to prove two line segments are equal. You look at some triangles or something involving those line segments, and then if you can prove that the two triangles are congruent, possibly there's a way of proving it. So here, there's a problem. See? Okay, you have a triangle BOD, but there is no triangle involving EF. Okay, so what do? You construct a triangle, a new triangle, whose one side is equal to EF. How do you do that? You can draw a line parallel to this. Let me denote this point by G. So I take AG. So you observe that I draw AG parallel to EF. Okay. Now we have two triangles. One thing that you observe is that AG is equal to EF. So whatever you want to say, so it is enough to measure AG instead of EF. They are equal. So can you prove OD is equal to AG? You have two triangles now. As OD as one side, AG as a side of the second triangle. Both these triangles are right angle triangles by your construction. Okay? And then in that triangle you see that this point or this line is equal to this line because they are sides of a opposite sides of a parallelogram. So if you can, and you see this angle is 90 degrees. Now if you want to conclude that these two triangles are congruent, all that you need to do is to give an argument that this particular angle is equal to this particular angle. Okay? Let us see how this could be done. Now what I do is I extend this line. If I extend this line, what do I get? It is a line parallel to BC. Okay? Right? And these two lines are parallel. This line is parallel to this line. Therefore, you can conclude that this particular angle is equal to this particular. That is one thing that you can conclude. Next thing that you can conclude is that, okay, these two lines are parallel. This line is parallel to this line, and this is something that intersects it, and therefore this angle is equal to this angle. So sum of these two angles is equal to sum of these two angles, which means angle BOD is equal to angle CAG. The students, please sit down and work this out completely, the details. So you have now two triangles in which OB is equal to AC because they are the opposite sides of the same parallelogram. Okay? These two angles are, that is angle ODB and is equal to angle AGC because they are equal to 90 degrees. This is how we have drawn it. The third one is we have proved that this particular angle is equal to this particular angle. And once you have proved that these two triangles are congruent. So these two triangles are now congruent. Okay? So two angles and one side equal. They are congruent. So you have now, I can write this, that triangle BOD is congruent to triangle what? CAG. Which implies OD is equal to AG. This is what we wanted to prove. But AG, this is equal to EF. Okay? Therefore, you have AD equal to EF. This is what we wanted to prove. OD equal to EF. Or in other words, OD we know, OD is equal to V1. Therefore, this is equal to. So EF is equal to V1. So what do you get? So this implies C1 is equal to A1 plus B1. Now it's almost child's play to prove that this is equally well true about the second coordinates. You will have to work in a similar way to show that C2 equal to A2 plus B2. What an elegant relationship that you are getting. Okay. Therefore, I can now replace this by the following. So we know it already. It is A1 plus B1, A2 plus B2. Right? So what have we done? We've taken two vectors. We have translated this into the coordinate system. We have introduced the coordinate system. And based on the coordinate system, we have attributed ordered pairs of numbers to the vectors. And then we have worked out the parallelogram law, looked at the diagonal, and then we proved that the coordinates of the diagonal are obtained by adding the respective coordinates of the two vectors. Beautiful result. Okay. This is again, you see, translating a geometric problem into a algebraic problem, because you see that this involves only addition of numbers, unlike in the geometric way in which we were looking at the resultant. Now it is quite easy to find the resultant. Okay. Therefore, let me see what. Let me just tell you what is the application of this. The application of this is the following. Suppose we go back to our original problem. You have OA, OB, OC, OD, OB. So 5 forces are active at a point. Now what you do is you introduce a coordinate system with the point of action as the origin. Okay. Now, once you introduce a coordinate system and the scaling on the lines, you have say this is A1, A2, this is B1, B2. I am assuming all the forces are linear force. Working in a plane, the same plane. Then this is C1, C2, this is B1, B2, and this is B1. These are the coordinates of these A, B, C, D, E respectively. What is the resultant? What is our procedure? Our procedure was pairwise drawing the parallelogram and then working out the diagonal, etc. You see that the resultant of this force, suppose I call that force OF. Suppose OF equal to OA plus OB plus OC plus OD plus OE. Then what about OF? So geometrically this is what it is. But what are the coordinates of F? The coordinates of F are, the point F has coordinates A1 plus A2 plus A5, A1 plus B1 plus C1 plus D1 plus E1, and the second coordinate is A2 plus B2 plus C2 plus D2 plus E2. That means by simply adding the first and second coordinates of the forces you can immediately write down the coordinate of the resultant. You don't have to do all these acrobatics. All that you need know is the coordinate representations of the force. In fact, in the more general scenario of three-dimensional forces, suppose you have vectors in space represented by the coordinates. So you introduce a coordinate system in the three-dimensional space, x-axis, y-axis, and z-axis usual, with the scale, with the units prescribed on the lines, and then every point is represented by a triple. And if you have forces like this, suppose these are three-dimensional forces, then what happens? A will be having coordinates A1, A2, A3. B has coordinates B1, B2, B3. C has coordinates C1, C2, C3. D has coordinates D1, D2, D3. E has coordinates E1, E2, E3. Then the sum of these forces is given by OF, where the coordinates of F are given by A1 plus B1 plus C1 plus D1 plus E1, comma A2 plus B2 plus C2 plus D2 plus E2, comma A3 plus B3 plus C3 plus D3 plus E3. So the triple can be obtained. Now, what I wanted to impress upon you is that now the addition of vectors is so simple. It is the parallelogram law that works. Physically, that is what works. This is not a mathematical invention. It's physics, or the physics of nature tells you that it is the parallelogram law with which vectors add. You can do nothing about it. That's how nature works. Okay? It's nothing artificial about it. So it has been experimentally verified. Okay. Now mathematically, we conceived this in the form of vectors, and through geometry you can solve this problem of finding the result, what you call the resultant of several forces by using applying pairwise parallelogram law. Okay. Then we found that if you introduce a coordinate system, then you can solve this problem in a much more simple way. That is, find the coordinates of the forces acting, and with respect to a certain coordinate system that you introduce, and then you see that the addition amounts to coordinate-wise addition of the vectors. Now this is it's a beautiful result that you have. You recall how powerful the particular experiment that you have been doing in your physics lab, which is also one of the secrets of nature. Okay. So we can now talk about in an abstract way, and now you see the problem has been resolved and simplified to the extent of simply adding numbers. It is as simple as adding numbers rather than drawing diagrams. Okay, right. So that problem is now solved. Now in another 10-15 minutes, I will just go to the central aspect of the problem that I was telling. You can represent lines in terms of vectors. Let us see what it is. Okay, let us take in R2. So we now take R2, or what you call R cross R, as a two-dimensional space. Okay. Now each point has, if you take a point here, say O, A, then A has coordinates A1, A2 by tuning. This distance is A1. This is A2. Right. That's the meaning of that. Okay, so every point corresponds to a vector. You can add vectors. Additional vectors is given by coordinate wise addition. Okay. Now what about scalar multiplication? Scalar multiplication is another process that you have. When you scalar multiply a vector, suppose you have a vector. What you do is when you scalar multiply this, what you are doing is you are scaling it. And in fact you can show that given a vector, you can generate a line using the vector v and represent any point on this as v times v. What is it? See, the vector v is represented by v1, v2. Okay. So what about tv? tv, you can show that this is equal to tv1, v2. Now you see that the line generated by v is given by the set of points tv, t belonging to. Okay. Let me talk later. Let's take out this picture. Then go to the next one. So what one has is the following. So you have a plane. You are given a vector. Not necessarily you can have vectors drawn in any one of the quadrants. Not necessarily in the first quadrant, but by habit I am just drawing that. So this is V, which means that this point is V1. Now I draw the line generated by the vector V. Then if I take an arbitrary point on this, this is given by V. That means this is a point with coordinates. Observe that when t is equal to 1, you get back your original point. Okay? When t equal to 0, you get the hypothetical 0 vector. Okay? And when t is greater than 1, then you get a vector somewhere here. That means you are taking the vector and elongating it without changing the direction. When you take t negative, then you are reversing the direction of the vector and elongating it or contracting it depending on what is the absolute value of t. Okay? So you get in fact the whole line generated by tv. So the equation of the line can be written as x equal to t. Okay? It's a line. So given a vector, there is a unique line passing through the origin generated by v, whose equation is given by this in this form: t belongs to R. Or as a set, it is the set of all x belonging to R2 such that x equal to t. Now v equal to v1 v2, then this means x equal to tv corresponds to two equations. One is x1 equal to tv1, x2 equal to tv2, where t is a parameter. Okay. Now let us eliminate t between these two. How do we eliminate t? See, this is an arbitrary point on this line. X is an arbitrary point on this line, fixed by the multiplying factor t or the parameter t. So this is the parameterized form of the line. Okay, t as the parameter. How do you get the equation of the line? Eliminate t between these two and get a relation connecting v1 sorry, x1 and x2. So you multiply the first equation by v1 and the second equation by v2, then you get, so first equation by v2 and the second equation by v1 and subtract, then you get the following form. So v2 x1 minus v1 x2 equal to 0. This is the equation of the line. I think it must be ringing a bell in your ear that the equation of the straight line is given by a1 x1 plus a2 x2 equal to, this is the general form of the equation. Equal to, say, b or something like that. Okay, where b equal to 0 is this form. So here a1 is given by v2, a2 is given by minus v1 and b is given by 0. This is the general equation of the line. Okay. So now the question is, so we are now restricting ourselves to the lines passing through the origin. Okay. So this is what you get. Now let me move forward further. Okay. So now what we have done is, given a vector, we have got the equation of the line generated by V. Suppose you are given a line passing through the origin. O given by a1 x1 plus a2 x2 equal to 0. Because you know that they pass through the origin, therefore this constant is equal to 0. Is it possible to find a vector V such that this is given by, this has the vector form x equal to, in the parameter. Okay. Let us see what we can do. You compare these two. Suppose it is of the form x equal to tv, then you know that this compares like this. That is, v2 takes the place of a1, v1 takes the place of a2. Meanwhile, we will also observe a thing. What about this v1, v2? v1, v2 is a specific point on this line. We'll make use of that. Suppose this is the line a1 x1 plus a2 equal to 0. What you do is, let us find out some point other than 0 on this line. Okay. So can you get a point on this line which is different from 0? I mean, we are assuming both a1 and a2 are not simultaneously 0, or we put the restriction that a1 square plus a2 square is not equal to 0. So that both a1 and a2 cannot be simultaneously 0. Because if they are simultaneously 0, then this equation does not tells you nothing. It becomes just 0 equal to 0. Okay, right. So we assume this. So this equation is true only when at least one of them is different from 0. Okay, so we make this assumption, right? This equation is given. We want to find out a v. So we find out some point on this line. Okay, For instance, you make an observation. You want to find out an x1, x2 that satisfies this equation. So let us give some value for x1. I mean, I don't want both to be 0. So if I take x1 equal to 0, then x2 is also going to be 0. That is the solution. So I don't want that to happen. For instance, you can take x1 equal to 1. So let us take x1 equal to 1. Then what is that you are doing? This is x-axis, this is x1 axis, this is x2 axis. So suppose this is 1. Then what I am doing is x1 equal to 1 is this line. I am finding the intersection of this point. What are the coordinates of that? Suppose I put x1 equal to 1, then I get a1 plus a2 x2 equal to 0. Therefore I get, okay, specifically I assume a2 is not equal to 0. That is without loss of generality. So that this condition is satisfied. If so, what do I get? a1 plus a2 x2 equal to 0. And that gives, since a2 is not equal to 0, I can divide by this. So I get x2 equal to minus a1 by a2. Okay, right? Therefore, 1 minus a1 by a2 is a point on the line. More specifically, suppose I multiply by a2, because if I multiply by a scalar, then this is what do I get? You observe that a2 minus a1 is a point on the line. Now you see, you can find infinitely many points on the line, take any one of them other than 0. This is possible for the purpose. So I take V to be equal to a2 minus a1. Now my claim is this: x equal to TV represents the same line as given by this. What do I have? I have x1 equal to what? Ta2, x2 equal to minus ta1. As before, you eliminate t between these two. Then what you get? You get a1 x1 plus a2. So the method that you have is this. Suppose the given is given in the analytic form. Choose a point on this line other than 0, 0, or that vector v, and then write x as tv. For example, suppose you have 2x1 plus 3x2 equal to 0. Then what do? You choose 3 minus 2 is a point on this line. You can just directly substitute and verify that this is true. Call that b. So you write x equal to tb. That means you get x1, x2 equal to t times 3 minus 2, which will give x1 equal to t into 3, x2 equal to t into minus 2. Eliminate t between the two. You get 2x1 plus 3. As simple as that. So you see that this is a point that you pick on the line. In fact, you see, this is not just one line that you can use. You can use infinitely many points other than 0, because if you use 0, you get nothing. Okay, TV is going to be 0. So you choose a non-zero point. So the restriction that you have is that choose V such that V is not equal to 0, but V belongs to the line. Okay, so that is resolved. So that tells us that we have resolved the problem. I think I'll take another 10 minutes and then finish it up. Okay. That tells us that we have resolved the problem a restricted form of our problem. What is it? We have now only looked at lines passing through the origin. What about lines, general lines? Any line, any straight line in arc can be of sides. Now you know that, take the plane. Suppose there is some line given whose equation is given by a1 x1 plus a2 x2 equal to say b. Okay, since we are not assuming that it passes through the origin, b may be different from 0. But if it passes through the origin, then b equal to 0. How do you put this in the vector form? Okay, right? This is the question. Before that, we do some exercise. You take R2. You are given a non-zero vector B. You can generate the line. This is x equal to B. What you do is you choose a vector A. Call this A. Choose a vector A. Okay. A does not belong to what do you do? Now we start adding A to any vector on this line. Any vector on this line is of the form x is equal to t. So what do you do? How do you add? So there's only one way in which you can add vectors. It is using parallelogram. Complete the parallelogram with this vector tb and a as the sides. So you get a point. You fix point, add to, you get a point. Now you take any point here and add it. You keep getting this. Essentially what you do is, if you allow this t to vary from minus infinity to plus infinity, you get this line whose equation will be given by x is equal to, is that clear? This is vector addition. This is a vector, this is a vector. Add these two vectors, you get a vector. Okay. So a general line can be conceived as the translate of a line through the origin. This is what I mean. See, you have a line through the origin here. Now what I am doing is, I am translating it parallel to get this line. Okay. So I transport it parallelly through the vector A to get the line. Okay. Let us explore this. What do you get out of it? Suppose into then x is equal to corresponds to two equations. What are the equations? We have x1 equal to a1t, sorry, v1t plus a1. Or in other words, what you have is x1 minus a1 equal to t v1, x2 minus a2 equal to t v2. Now eliminate t between the two. It's very simple. You multiply this by v2, this by v1 and subtract. So if you do that, this is what you get. v2 into x1 minus a1 minus v1 into x2 minus a2 equal to 0, or you get v1 x1 plus v2 x2 equal to what? You get v1, you take it to the other side, so you get v1 v2 a1 minus v1 v2. This is once again of the form a1 x1 plus a2 x2 equal to c, where a1 is equal to v1, a2 equal to v2, c is equal to v2 a1 minus v1 a2. Okay, so you see that once a line is given in the form x is equal to tv plus a, it can be written in the analytic form something like capital A1 x1 plus capital A2 x2 equal to capital C. Okay. Now let us use this idea to work on this. I mean, what is the idea? Idea was, what we did was, we had a line here passing through the origin, translate it to get another line. So suppose you are given a line, now we reverse the process. Suppose you are given a line here, something like a1 x1 plus a2 x2 equal to c. What do? We translate it parallelly to get the line through the origin. Then you see that the equation of the line is a1 x1 plus a2 x2 equal to 0, right? So given the line a1 x1 plus a2 x2 equal to c, the line parallel to it through the origin is given by a1 x1 plus a2 x2 equal to 0. Okay. Now this you can obtain the vector form. Okay. For this you can get the vector form that we have already done. What you do? To find a point on this and then write this as x equal to tv. What do you do? Okay, let us do that. So you see that minus a2 a1 belongs to a line, or a2 minus a1, you want you can write minus a1 belongs to L, the line L. L1. Okay. Now suppose you denote this by V, then you see that x equal to V, this equation of the line. Now we want to translate this. We want to translate this parallelly to get the other line. So what do? Choose any point on this line. Okay. Call that B. Suppose I call this B. Then this particular line is going to be x is equal to B plus B is a point belonging to. Okay. Let us explore this. Take an example and then work it out for this. I have 2x1 minus 3x2 equal to 1. Okay? Suppose I want to get the vector form of this. What do? I take the line parallel to this through the origin. So that is 2x1 minus 3x2 equal to 0. So let me find out V. V should be a point lying on this. So let me take a point lying on this. What do I have? You take 3 2. Comes to the point 3, 2. 3, 2 lies on this. You can directly verify 2 into 3 is 6. 3 into 2 is 6, and there subtract when you get 0. So this belongs to 10. This is the line L1. Okay. Therefore, what is the vector form of this? The vector form of this is the x is equal to t v. X is equal to t into. So this is the vector form of this. Now, how to get the vector form of this? Now you see. You work out what this line is. Okay. Right. It passes to the point 3, 2. So 1, 2, 3, 2. This is the point. This is the line L that you have. What about L1? See, it passes through the point. See, you take x1 equal to 0. x1 equal to 0 is this line. That will give you x2 equal to minus 1 by 2. Pass it through this point. Draw the line passes. Okay. So let us work that out. Okay. So we find out a point lying on this one. So one of the choice that you can make is you can find a point. So you take x1 equal to 1, x1 equal to minus 1, x2 equal to 1. x1 equal to minus 1 and x2 equal to 1. Then what do you get? Minus 2 minus 2 x1 equal to 1 x2 equal to 2 x1 equal to 2 and x2 equal to 1. Take the point 2, 1. Okay. So you take the point 2, 1. 2, 1 lies on L1. Is it true? 4 minus 3 equal to 1. So it lies on that. Okay. So you take this as your. Now what is the equation of the line? The equation of the line is x equal to tv plus c. So let us write this out. What is the equation of the line? X is equal to t times v2 plus 2. Okay. This gives pair of equations. x1 equal to 3t plus 2, x2 equal to 2t plus 1. Okay. Eliminate t between the two. What do you get? Okay. You multiply this equation by 2, multiply this equation by 3 and subtract. So you get 2x1 equal to 6t plus 4. Multiply this by 2 and subtract. So you get okay, 3x2 equal to 6t plus 3 and subtract. So you get 2x1 minus equal to 6t cancels. So t gets eliminated. So you get 4 minus 3 is 1. You are back to. Okay. So the secret is this: you take the line, move it parallelly to find the line parallel to it through the origin, and you know that the geometry tells you that there exists a unique point passing through the origin parallel to a given line. Find the equation of that. And its equation can be, its a scalar form of the equation can be written easily. It is a1x1 plus a2x2 equal to 0. Get a vector form by choosing a vector and then translate it back. So you find out through which vector you have to translate it back parallelly to get the equation. So this is the form of the equation that you have. So this is the vector form of the equation, this is the scalar form. Okay. I want to make two remarks. The remarks are the choice of, in this representation, the choice of B and A are not uniquely determined. In fact, they are determined. There may be a V1 working on it, there is another V2 working on this, and so on. So this is possible. So this is not unique. So the choice of V and A are not unique. Okay, so I'll just take a couple of minutes and make one very interesting remark. If you can catch it, it's good. Okay, let me look at this one. X equal to TB plus T. What does it give? If you take T as a time parameter, you see that at, and this describes the position vector of a particle moving. Okay? What does it give? At t equal to 0, you are at the point A. So this is the vector A. So you are at this point. At, and you see that it has got certain slope described by the vector V. Okay, so an arbitrary vector, the vector V is obtained by a line on the line parallel to this, and this is your V. This is the conclusion. Now you see, we call the equations of motion. Xt is Tv plus A. Think of a particle moving with velocity v, which is at t equal to 0, x0 equal to t. That is the initial position. Then you see that dx by dt is given by v, which is the velocity of the particle. Okay, so this is the description of a particle moving with velocity v and passing through the point A at the time t equal to 0. Okay, so that's the dynamic picture of this. Right? Now I just usually give this analogy. You would have seen the railway lines and the trains traveling on this. Okay, so you have a railway line, there's a train passing on this. Okay, suppose there is a train passing on it at velocity v1. Then you see at time t equal to 1, you see the particle on v1. At t equal to 0, you are at the origin. Suppose this is a station. Okay, and the train is moving in this direction, and this is the vector v. Then this is like this. After 2 units of time, it is at 2v1, etc. After t units of time, it is at the point t. That is the first express train or moving train. Suppose you take another train moving with a slower speed, something like v2. Then you see that After, suppose both of them start at the same point, you see that one would be lagging behind. And it's travel like this. So each position will be something else. Nevertheless, you see that it will describe the same line. What is the relation between V1 and V2? V1 has to be a scalar multiple of V2. That is the condition. Then they travel along the same line. Okay? So any choice of V1 or V2 will be an ideal choice. That is why what I said, when you want to put this line in the vector form, you can choose a vector which is not equal to 0 lying in this line. Okay? Right? And you can even choose something in this direction. Suppose there is a train moving in this direction, then your V is going to be in this direction. And then TV will be some point here. So that means your motion is in a different direction. Therefore, the vector representation is essentially very versatile. While the scalar representation only talks about the rail on which the train is running, but the vector representation actually describes the running of a train, because it gives the versatility. It talks about all sorts of trains that are running on this railway line. With these few words, I thank you once again for this beautiful opportunity. I hope you could make out whatever I said. Thank you very much.